Up until now, we've talked about electric charge. There's two types. There's positive and there's negative electric charge. And we talked about three ways to give an object a charge, either be friction, contact, or induction. And we said if they have charge, they exert force on each other. So if they are opposites, they attract, likes, they repel. Now the big question is, how are they attracting or repelling each other when there is no contact between them? So how is this positive charge making this negative move towards it with no contact? And the way we explain this is through a concept called the electric field. And the electric field causes an electric force. It would be similar to this. Let's say that I, as your teacher, ask you to stand up. So I say, stand please. And you, as a conscientious student, do what I ask, and you stand up out of your seat. So I have made you move without having any contact with you whatsoever. And the way that I did this was through a signal that I sent. It was my voice. So I send this signal to you, and that causes you then to move. Well, the same thing is happening with electricity. These charges send out signals causing electric forces, causing them to move. But these signals, of course, are not audible. It's not like we can hear these charges talking to each other. But it's the same type of thing. So an electric field is something that permeates the space around a charged object and in which another charged object experiences an electric force. So it is the signal that these charges send out, causing the other charges around them to move. Now it depends on two things. It depends on the strength of the charge sending the signal, and it also depends on the distance from that charge. So continuing with my analogy, it's similar to this. Let's look at the strength first. Let's say that a 7-year-old tells you to stand versus a 300-pound linebacker telling you to stand. Chances are the 7-year-old tells you to stand, you might not do it right away. You might question the child, why are you telling me to stand, for what purpose? If it's a 300-pound linebacker and tells you to stand, you're more intimidated and you might jump out of your seat right away. So the bigger the charge, the more signal there is, the more electric field there is. It also depends on distance. So continuing again with my analogy, let's say that your mom is sitting in the living room with you and tells you, would you please clean the room? We have company coming over later. You probably say, yes, Mom, and proceed to clean up the room. However, if your mom goes to the store and then calls and says, oh, by the way, I forgot to say something, there is company coming over, could you please clean the living room? After hanging up the phone, you might not clean the living room right away. Because your mom is further away, you're less apt to do what she wants at that very instant time. Of course, you'll get to clean the room, get to cleaning the room, but maybe not right away. And so the further the charge is from this spot, the less the field is. So the further away, the less the field. It's an inverse relationship. Now, the symbol for electric field is E for electric field, and the units are newtons per coulomb. We have two equations. The electric field is K, which is Coulomb's constant, same as in the electric force equation. So it is 8.99 times 10 to the 9th newtons times meters squared per coulomb squared. So it's this Coulomb's constant times the charge divided by the distance. R is again the distance we are from the charge squared. There's a second equation, that is the electric force is equal to Q times E. It's equal to the charge times the electric field. Now we always want to make sure we have the right units. So based on our units for Coulomb's constant, we must have charge in coulombs and distance in meters, and the electric field should be in newtons per coulomb. Now the two charges in the equations are actually different though. The charge in the first equation is the charge causing the field. Continuing with my analogy, it would be the teacher. This would be our charge in that first equation. In the second equation, Q sub 0 we call the test charge. This is the charge being moved by the field. So the student is considered the test charge in our analogy that we had used earlier. Now notice here that in this first equation you only need one charge. A field exists if there's just one charge present. So even if the student is not there, and I say please stand, my voice still exists. The signal still exists even though there's nobody there. I can get out a meter and read the decibel level at this spot even if nobody's present. Now when representing electric field, we can draw something called electric field lines. Electric field is a vector, so it has a direction, and the direction is that it points away from positive charges and points towards negative charges. So we have the depiction over here, positive charge with the electric field pointing away, and here we have a negative charge over here and a positive, and we can see it points away from the positive towards the negative. Now, since positive charges move away from positive charges, and electric fields point away from positive charges, that must mean that positive charges move in the same direction as the electric field. So if I were to place a positive charge at this spot, it would move in the same direction as the arrow. It would move that way. Negative charges move in the opposite direction of the electric field. So if I were to place a negative charge here, it would move in the opposite direction of the arrow. It would move to the right. The number of field lines is proportional to the strength of the electric field. So we can see in this blue diagram, right here the electric field is very strong because the charges or the electric field lines are closer together. But over here, we can see that the electric field lines are further apart, and so the electric field is weaker at that spot. Next, no two field lines can cross each other. If it points in the direction a positive charge can move, a positive charge cannot move in two directions at the same time. So you can't have field lines cross each other because it would mean that the charge would have to move in two directions at once, and that's physically impossible. Also, the electric field inside a conductor is zero. So if I were to take a conductor like that Van de Graaff generator, and I would place a charge inside that conductor, it would not move in any direction if I place it and let it go at rest. It would not have any force exerted on it, and so it wouldn't move in any direction, no matter where I place it inside that conductor. And finally, charge accumulates on the outside of the surface of a conductor. And this is why we are safe inside of a car during a lightning storm, because as lightning were to hit the car, it would stay on the outside of the car, and we'd be safe on the inside. Also, more charge accumulates where the radius of curvature of the surface is smallest, meaning that it always accumulates and leaves the surface at a point. Wherever it comes, if there's a deformity, if it kind of comes to a point here, there's a deformity, more charge will be located at that point than other points. So again, the electric field is a signal that causes the electric field.